Oh, hey everybody, I'm just reading this label. It's a container of salt, which by the way, doesn't just have salt, which is NaCl, the formula for salt. It has potassium iodide, which helped a problem. Generations ago, a lot of people had swollen thyroid glands, or what we call a goiter. Anyhow, that problem virtually disappeared when they figured out they could put potassium iodide into the salt and give people what they needed, which was, by the way, less than 1/1,000,000th of an ounce of iodide. So that's a formula that occurs between potassium and iodine, and because both are in the same families, sodium and potassium, chlorine and iodine, they have similar formulas. That's an ionic compound, metal-nonmetal. And it turns out there's specific ratios in which those compounds can occur, and we're going to talk about all of them right now. Welcome to Ionic Compound Formulas Boot Camp, except it only lasts like 20 minutes, maybe 23. We'll see. Let's go to work, folks. Hi gang, what's shaking? What's poppin'? Mike here, and notice I started off today's lesson right where we ended off. Kind of one of the most important things, a pattern, is that on the fringes of the periodic table you find a lot of those elements adhere to this rule, that is the octet rule. Now remember, I go ahead and I label my periodic table differently. So the main group, we're going to give these folks a break, these little rogue troublemakers, the transition metals. We're going to just deal with the main group, which are the outer ends of the periodic table. So groups 1 through 8. If you number the periodic table the old school way. The reason we're going to re-hit this is we talked about stable ions last time. Well, we're going to talk about bonding. This is one of the most important concepts, and that is, this is how molecules happen. Why do atoms not stay by themselves? Well, we've established that. That's because most of them aren't stable by themselves unless they're noble gases. Then they already obey the octet rule. So we're going to talk about how bonding occurs, and there's two classifications generally about bonding. And this is ionic and covalent. But what happens is, covalent's the old school term back when your friend Mike went to school back in the old days, and now that term is also being sort of replaced by a more hip term called molecular. It means the same thing. I like the term covalent for a reason I'll talk about in a little bit. So here we go. What's the difference between ionic and covalent? And the only thing you need to keep in mind is that little staircase that I outlined on the periodic table. A lot of periodic tables, you'll see them colored differently. Well, and then that staircase will be there. But ionic is bonding between metal and non-metal. So you should be able to look at the formula of something, and now we're going to talk more about formulas. But if someone says, hey, NaCl, that would be a metal, sodium, with a non-metal. And so you'd say that's ionic bonding. That's all you need to know right now. Covalent is between non-metal and other non-metal. So you would see someone say, hey, CO2. Carbon dioxide, or water. That would be covalent bonding. And once again, don't panic. All you need to know is which side of the staircase each participant is on. A little more detail though. Ionic bonding involves the transfer of, guess which part of the atom? The stuff that's loosely bound, electrons. Transfer. That means atom A is not obeying the octet rule, and neither is atom B. And so one atom just goes and gives electrons to the other. One of them needs to lose electrons to obey the octet rule. The other one needs to gain electrons to obey the octet rule. So yeah, pretty simple. This is not simple. This is going to be a 18 video discussion later on in the semester. This is sharing of electrons, and this is much more complicated. So for example, you could say to me, hey, Y is something like CO2, and why is there a carbon monoxide and a carbon dioxide? And I'd say, well, geez, folks, that's a really long story. But it's a not so long story to say that the stuff in table salt is a 1-to-1 ratio, and the stuff that you sprinkle on your driveway to melt ice is not a 1-to-1 ratio. And that's what we're going to talk about next. But so far, you can now categorize any compound you see, or maybe it isn't even a compound. Maybe it's an element. If it's an element, it usually had to be something like this, right? But there's bonding there. So hold on for this. That's not the subject of today. We're going to do ionic bonding to death today. Well, that sounded negative, but we're going to do a bunch of ionic bonding. And so remember, it all stems from the octet rule. We're not just, this is not something you just kind of wing it, folks. You can't just write formulas. It's not like, write whatever formula you want. This is not freestyle beatboxing here. There's specific rules, and they're really pretty simple. And so we'll talk about the formulas of ionic compounds right now. All right, so you saw me reading my bottle of, my container of iodized salt. That's got potassium iodide in there. So let's go through the kind of thought process of when someone asks you, what's the formula between potassium and iodine? So first step is you have to say, what's it got to do to obey the octet rule? So what's going to happen is K is going to become K plus, because it's in group 1, which is the one with lithium, sodium, potassium, rubidium, and all those lose an electron, or if you just follow the rules, the group number is the positive ion that they make. Go over to iodine. Iodine is not stable as itself. It's in group 7, so 7 minus 8, that makes a -1 charge. And you know what really happened there, folks? What really happened is the way that that occurs is not just a magic trick like I made it seem. Potassium's going to go ahead and give its electron to iodine. It will become a negative ion. Potassium will become a positive ion. And now the way we think of this is we have those charges are going to attract each other. This is what we call an ionic bond. It'll be an ionic compound. Positives and negatives attract, very strong attraction, and that is a formula we would write as Ki. Now actually, let me be really specific here. When we write a formula, we write that in the order of the periodic table. So we put metals are on the left side of the periodic table, and iodine is on the right side, so we keep it in that order, and that's why the K comes first and then the I. And then what we have here is really, you've seen formulas where it's like H2O. Well, this would be like K1I1, but what we do is when there's a 1 there, we just kind of leave it off, and that makes things a little bit less cluttered, if you would. Now let's take that potassium and switch it out for a magnesium. So let's say magnesium runs into iodine. What formula are they going to make? So same process here. Yeah. Mg is in group 2 though. And group 2 is stable as a +2 ion. Iodine is stable as a -1 ion. And so what happens here is this can't work out the way the previous example did. And so what needs to happen is there needs to be a positive for every negative. And that's because this has got to give 2 electrons to something. And if it gave the 2 electrons to iodine, that one iodine, it would be I2 minus, and that would be gaining too many electrons and not satisfy the octet rule. So there's a bunch of ways you can think about this when we go from this stage, which is the starting stage. So you're not just winging it. You always say, how is this going to make a certain ion, and how are they going to recombine? A couple ways you can think of it. I'm going to give you about 3 different ways you could think of it. Charges have to cancel. Cancel. In other words, they got to have a cumulative sum of 0. And then the other way that they think is, okay, going from formula to whatnot, you switch the numbers. That's another way to think of it. Switch numbers. Here's the way I like to think of it as well. If you really, really start freaking out, just do this. Mg plus, and then I minus. You see how that ain't going to work out? How's it going to work out? I need 2 in order for every positive to have a negative, and therefore this positive will have a negative, and this positive will have a negative. And now I don't need 3, I don't need 1, but the formula, no matter which way you look at it, is going to be Mgi2. Mg1, if you will, I2. And there is no 1-to-1 ratio there that is stable, because either I would have to have a -2 charge, or and magnesium would have to have a +2 charge. That don't happen. So the only allowable formula between magnesium and iodine is going to be this 2-to-1 ratio. And so this is the only formula. And that means we have not only proved the formula that exists, we have disproved many others. So here we are over here. This is the wrong thing. Make it, frowny face with a goiter. Sorry. Okay. And that is that there is no MgI, there is no Mg2I, there is no Mgi3, ain't none of that. If there is something like that, ain't stable, doesn't obey the octet rule, doesn't happen. See, so ionic bonding is really picky. It's got to be equal number of electrons gained and lost. Everything's got to obey the octet rule, and that's what gives rise to the certain formulas that occur. So let's do a little bit of practice and get good at this. Oh boy, look at that. We're going to take 3 elements that are metals, 3 elements that are non-metals, and we're going to figure out the formula between all of them. So that's going to be 9 different compounds. And notice what I did not do yet is I did not write the stable ion that everything formed. One thing I did do is I was a little predictable in how I wrote them out. I didn't randomize it. But I have lithium is in group 1. Barium is in group 2. Now look, hey, I'm not just, I was reciting that off the top of my head because I've done this for years. But look, there's barium, group 2. Over here is aluminum, or if you're from Australia, you say aluminium. I don't know why. I don't know, it's like UM is not an sound. I don't know if they eat something that tastes good, do they go, yum, yummy, that's yummy. Sorry. So then what we've got is those groups 1, 2, 3. Well, hey, let's go fix this here. This is going to be, what's the formula between these ionic compounds? And I'm going to go ahead, group 1. Group 2, this is just the octet rule. Group 3, okay. Notice there's no noble gases because they don't do anything. So this is group 5. Nitrogen is in group 5. right? Oxygen is in group 6. Fluorine is in group 7. 5 minus 8, or it needs to gain 3 electrons for it to have as many electrons as 1, 2, 3 neon. Oxygen is its neighbor, only needs to gain 2. Now, if you like rules, it's just the group number minus 8. So 5 minus 8, 6 minus 8 is negative 2 minus 1. Now we're going to go make formulas. And you're going to do whatever one of those ways you like. But you can tell that lithium and nitrogen, if you get good at this, you've done them all. But that can't happen in a 1-to-1 ratio. You flip the numbers, whatever, a positive 1 and a negative 3 can't go together. You're going to need 3 lithiums in order to make that work. So whatever way you like to do it, folks. Switch the numbers. I'll explain how that could be a little bit dangerous in some cases. But let's go with switch the numbers. Li3N. That is the correct formula for the ionic compound between lithium and nitrogen. Same kind of thing with oxygen, except you only need 2. I need an L. Here's one way to look at it, right? Maybe you like this way. Maybe you like this. Li plus O2 minus. Let's not make it 2 minus. Let's make it minus and minus. Right? That's the same thing as writing 2 minus. I need 2 lithiums to match a positive with a negative. This would be Li2O. All right? And lithium fluoride. Now, you know what I want you to do? I want you to finish that. And I will give you the answers momentarily. Fill in the rest of that table. Make sure you're canceling all the charges, and I will cough up the answers next. And there it is. Those are your answers. And I don't know which style of figuring out the formulas you like. I want to talk about the flip the numbers thing. If you do like flip the numbers, let's go to barium and oxygen. So let's go over here. Barium 2 plus, oxygen 2 minus, right? Now remember, you always kind of, you're not just winging it. This is from the fact of what group they're in the periodic table. If you do the flip the numbers, you would get Ba2O2, right? And so if you like that, that's fine, but you have to boil it down to its simplest whole number ratio, and that's why that'd be BaO. If you like to do the match the charges thing, then you would just see that combines in a 1-to-1 ratio. So practice this, folks, and make sure you understand what's going on. And boy, I hate these 3 to 2s. They kind of get me. But you know, hey, if you have to flush it out, really simple, Ba++, right? And then N minus minus minus. And then you kind of just go through some trial and error here. You know, nope, that's 4 to 3. And that ain't gonna need more of these. Oops, now I overdid it. That's a 4 and a 6. But then boom, I got 6 positives and 6 negatives. Match them up. That's how you do it. Ba3N2. And so what you find out is, you know, these are the only ratios that nature allows. And so you not only prove that those are the 9 formulas, but you proved there's a gazillion other formulas that don't happen. I don't know, take this example here. ALF3. That means there ain't no ALF2. There ain't no ALF. Well, unless you are talking about the 80s TV show, but that thing got canceled back in the 80s. Alf did, and he ate cats, and I have a cat, so that ain't happening. Okay, I got one more thing to talk to you about, and that is these weird ions called polyatomic ions. I am not a person who makes people memorize them, but let's talk about one more type of ion next. All right, folks, polyatomic, more than one atom ions, are just molecules that have either lost or gained electrons, and now they bear a charge. They behave this thing here, they have names. Maybe you've heard of them. Ammonium. These have names, and this behaves just like a sodium does in terms of how it combines with other ions, all right? They have names. I want to talk to you about that, but we're going to talk about naming next time. But sometimes what they'll do is they'll have an 8 at the end. All these have 8 at the end. Oop, not this one, sorry. A lot of them have 8 at the end. So this is nitrate. You've probably heard that. Maybe you're a gardener and you've heard of ammonium nitrate. That's fertilizer. I use that to fertilize my blueberry plants. This is called nitrite. So the one that has more oxygens usually gets the term 8 and an ite, but we're not going to make a name of them. I want you to be able to make the combinations of the two. So let's go ahead and I was reading my package of ramen noodles, and it said it had, I was reading my package of ramen noodles, and it said it had sodium and carbonate, a compound between that. So how would we write this? Same way you would write the other ones. The metal goes on the left, you'd switch the numbers or what? You'd see you need 2 sodiums, and so you would write Na2CO3, and that's it. Just like if it, so you treat that CO3 2 minus just like it was an O2 minus or an S2 minus or anything that was a 2 minus, and then therefore they'd need to be paired in a 1:2 ratio with sodium. So now what happens when you got more than one of these things? So you got a calcium and an NO3 minus. When you have more than one polyatomic ion, the way you write it in a formula is the same ratio. You'd need 2 of these and 1 of those, but you put a parentheses around it. You don't do that when there's just one. So this would be Ca parentheses NO3 2. And of course you see that you would need 2 NO3s to satisfy the positive 2, and that would be the formula between Ca2 plus, calcium, and what they call the nitrate ion, NO3 minus. That could happen the other way around too. There's actually not many polyatomics are positive, but there's one, the ammonium. And if I had that with a carbonate, CO3 2 minus, you would see that would still, don't worry about what's in front of the positive or negative. Just concentrate on what the charges are. And it don't matter what the positive 1 is and what the negative 2 is, you got to have 2 of the positive 1s and 1 of the negative 2s. And so when you come up with the formula the way you know it needs to be with 2 of these and 1 of those, then you would have to write it with parentheses around the NH4 plus and then CO3. Fair enough? Sorry, I know this lesson is quite a bit longer than maybe the other ones were, but this is important stuff, gang. So that's why we're going long. So I want you to write the formula that occurs between the 4 compounds that would occur between, and we gave you the charges because now here's the thing, polyatomic ions, we have to get into great depths of covalent bonding before I can explain to you why C2O4 2 minus is a 2 minus and not a -1 or a -3 or a +1. So you can consider that some sort of magic trick at this point. Just accept it for what it is. But we're going to go ahead and write the compounds formula that exists between those. Take a few minutes, hit pause, and I'll see you back here, and this will be our finale for today. Hey-yo! There you go. That is the formula of all those. And if this is tripping you up, make a comment, get at me, but it's just make the positives and negatives equal. That's all it is. And then what the subscripts are in the formula is just what's dictated to make them equal. By the way, this is called the oxalate ion. If you've ever had, you or a loved one has ever had the joy of having a kidney stone, you need to find out whether they're a ionic compound of calcium and oxalate, and then you need to avoid oxalate in your diet, which is a bummer if you like spinach or tofu or anything like that. This is called phosphate. But we'll get into naming next time. So we know how basically to write any kind of ionic compound, metal, non-metal, that you will see. These non-metals that you see as the negative ions, they happen to be polyatomic ions. Sometimes they're individual atoms, which the periodic table is your friend, and that's how you figure that out. So remember, it all boils down, you gotta just, you won't freak out if you realize you got a starting point. It all starts there. That's what determines the charges on all the positive and negative ions. That's what determines the formula. It's the same story, folks. We're just telling you the same story, just it's getting a little bit deeper as to the manifestations of the octet rule. So see you next time, and we're going to give these compounds their names. Take her easy. Have a good day.